So, in the third lecture we will talk about space curves, that is curves in R3, and in the process we will also complete something we have left undone for the planar curves. So, first let us see most fundamental difference between curves in R2 and R3. I have in the first lecture, suppose in the first lecture I have given this example circle, let us say gamma s equal to cos s sin s, circle with radius 1, unit speed parameterization, right. Also we have talked about this fellow, which is gamma s equal to cos s sin s s, which is a helix. Now, if you calculate the sine curvature of circle, this will be 1, and similarly for the sine curvature of helix, this will also be 1. So, helix, what happens? Helix is a circle on xy plane and it spirals on z axis, and so a circle can never be mapped to helix by a rigid motion. What do I mean by a rigid motion? Okay. A rigid motion, let us say in plane, is a map from R2 to R2, which is M, which is given by a translation by a vector composed with, so first rotation and translation, or first translation then by rotation. So, what is translation? Translation is, suppose I have vector x y is the vector x y plus a in R2, and what is rotation? This is simply rotating by an angle theta, x sin theta, y cos theta. So, such a thing is called a rigid motion. So, now you can imagine that if I have a planar circle and I translate it or rotate it or whatever I do, I cannot make it a helix. So, both of them, but has sine curvature, same sine curvature, but no rigid motion can map a circle to a helix. But whereas I have this theorem which is a part of assignment, that suppose gamma is a unit speed curve in R2 in the plane, whose sine curvature is k, and if gamma tilde from some other interval alpha beta to R2 is another curve, another unit speed curve with same sine curvature k, then there exists a rigid motion m from R2 to R2 such that gamma tilde s equal to n gamma s. This is what I meant by in the last lecture, that any planar curve is determined by its sine curvature up to translation and rotation, that if two curves in a plane has same sign curvature, then one can be mapped to another by translation and rotation. But as you see just in the previous example, if I in R3, if I have same sign curvature of two curves, I can never map through any rigid motion of R2 or R3 a circle into a helix. A circle cannot be made to a helix by any transformation, any translation and rotation. So, study curves in R3, we need to have some more quantities to define. So, some more invariance of the curve. So, let gamma from AB to R3, okay, let us make it AB this way, be a regular unit speed smooth curve. Okay. What we have done before, that its unit normal is equal to Ks by T dot S. This we have defined before, right? Ks is, we have defined this way, and you know eta S and Ts are perpendicular. Now, consider this vector B S equal to T S cross product with eta S. So, this is perpendicular to both T S and eta S, right. At any point this vector is perpendicular to both unit normal and unit tangent vector. This fellow is referred as, so this has a name, is called binormal. Of course, this is a unit vector and any unit vector. So, B dot S is perpendicular to B. Now, B is perpendicular to both T S and eta S. B dot S is perpendicular to B. Okay. Now, you see, if you use this thing that I have used ds of two function, I have E, U and V, and if I look at their cross product and if I take the derivative, this is du ds cross product V plus U cross product dv ds. So, use this, what I get, B dot is equal to, from this part, equal to T dot, I am suppressing the S part, plus T eta dot. I use the previous formula, this is K eta sine curvature. Okay, let me put the S. Look at the formula for sine curvature, cross eta S plus T cross T S cross eta dot S, let us keep it. So, this will tell us that B dot S is also perpendicular. Now, this fellow is 0, right, because K S is a quantity, scalar quantity, and I am taking cross product of eta S with eta S. Cross product of A with A is 0. So, this is equal to T S cross eta dot S. So, what it says, B dot S is also perpendicular to T S. So, it is perpendicular to B, is perpendicular to T S, and B is perpendicular to T s and eta s, that implies B s dot is equal to some constant at point s. For some reason I put a negative mark here, you will see why. This fellow tau s is referred as torsion of gamma. See, this makes sense only in R3, because if I take in R2, this cross product does not make sense. If I have two vectors in R2, that cross product does not make sense. So, the torsion only makes sense for curves in R3. So, what is this? So, what is this quantity? What does this measure? Okay. To see this, let us say I have a curve gamma, and suppose I have unit speed, regular, everything smooth, and this is identically 0. So, I want to see what torsion measure. So, let us see if I have a curve whose torsion is 0, what does it say? What does it mean? B dot s, which is minus tau s eta s, this is 0 identically. That means B dot s is 0 identically. What does it say? B s is a constant, say equal to B. Now, T s dot B, B is binormal is perpendicular to both T s and eta s from the previous one. Binormal is perpendicular to T s and eta s both. So, this and B s is identically B. So, T s dot beta is 0. What does it say? B is a constant. What is T s? Recall T s is gamma dot s. So, therefore, d d s as gamma dot B, this is 0, implies gamma dot B is constant. Say C. Gamma dot B, so gamma is a curve in R3, listen to me again, gamma is a curve in R3 whose dot product with a fixed vector is constant. That gives gamma is planar. Why? If I have a curve in R3, I cannot have a fixed vector unit vector B whose dot product with it is always constant. Why is so? So, why? Just think about it. If I do not have I have a proper curve in R3, so all the 3 coordinates are, it cannot be all the 3 coordinates are 0, I mean one coordinate cannot be 0 all the time, then it cannot have a fixed vector whose dot product with it is 0, because dot product is an angle geometrically. So, B is a vector in R3. So, I am explaining this y part, you think about it yourself also. B is a vector in R3, gamma is a curve whose angle with the fixed vector remains same. So, gamma has to be planar. Planar in the sense that it may not be the plane in the usual sense, it may be a tilted plane. Now, also again, suppose gamma is planar. Okay. So, then there exists a vector, unit vector A, such that gamma dot A is constant. You just take the vector which is perpendicular to the plane of gamma. So, that means gamma dot A, this is also 0, that will give you t dot a, t is 0, and if I do another derivative, t dot a is also 0, but t dot is sign curvature eta s. So, sign curvature eta s a dot equal to 0. Assume k s not equal to 0 for all s, that will give you eta s dot a equal to 0, that will give you t and eta both are perpendicular from this and from this, perpendicular to A. Therefore, binormal by definition this is equal to A or minus A, because binormal is the unit vector which is perpendicular to eta s and T s, and A is a unit vector which is perpendicular to T s and eta s. So, binormal is either A or minus A. Therefore, B dot s is 0, which will imply torsion is 0. So, what it says? Suppose I have a planar curve with nowhere vanishing curvature, 0 torsion, then sorry, I have a planar curve with nowhere vanishing curvature, then torsion is 0, and on the other hand, if I have torsion is 0, then the curve is planar. So, what does torsion measure now? Torsion precisely measure how much it is away from being a planar curve. Okay. So, that is the geometrical interpretation of torsion. So, let me put an example here. Again the helix, let us say B s. Here is a problem for assignment also. Torsion is equal to gamma dot, gamma double dot, dot gamma triple dot. Count the number of dots, important. Gamma dot, gamma double dot square. This is a formula for torsion. So, this formula will give us for this particular curve, this helix, tau s is b by s square plus b square. Hence, if b equal to 0, then torsion is 0, and therefore, gamma s is a cos s 0 0. This is a circle in the plane. So, this example was to illustrate that a planar curve, a curve is planar in curve in R3, this is planar if and only if the torsion is 0. This torsion measures that how much it lifts from the plane. Now, you see I can to make the invariance of a curve. So, in plane sine curvature is the complete invariance. So, sine two curves unit speed has same sine curvature means by some rigid motion I can map one into another. What do I do for curves in R3? To do that, there is a very important tool in this subject. I will write it down. So, what we have seen? We have seen that T dot is sine curvature dot eta s. We have also seen B dot, the binormal S, is minus tau s into eta s. So, I dot T dot s, B dot s. Now, we have T s eta s B s. At any point S, this is a right handed orthonormal basis for R 3, in the sense that T s is eta s cross B s, eta s is B s cross T s, B s is T s cross eta s, correct. Now, and they are all orthonormal unit vector. So, but now I know T dot s in terms of sine curvature and eta s. I know B dot s in terms of sine curvature and eta s. So, what is eta dot s? Well, I know eta equal to, just now I wrote B s cross T s. So, again using the previous formula, eta dot s is equal to B dot cross T s plus B s cross T s dot, which is equal to, if I use formula, above formula, T s cross T s plus K s B s eta s, that is simply minus K s T plus T s B s. How do I get that? Check. So, what do I get? I got T dot equal to K s T s is eta K dot s K s eta s, eta dot s equal to minus K s T s plus B s, and B dot s equal to minus tau s into eta s. I am writing it in for a purpose, because I have to write it as a matrix, okay, or in matrix from what I have 0 K s 0 minus K s 0 tau s 0 minus tau s 0 T s eta s for each point B s equal to T dot s eta dot s B dot s. So, this is a relation between derivatives of the quantity T s eta s beta s, relation between the vector T s eta s B s at any point to their derivatives, and this is a famous formula called Fredette-Sarré formula, and this will be used to prove the invariance. So, we will prove in the next lecture that this quantity sine curvature and the torsion determined a planar special curve up to rigid motion of R 3. So, let us wait for the fourth lecture.